Hi, my name's Brian Waite, and I'm going to talk to you about differential privacy. And when I say differential privacy, I'm really basing the majority of this discussion on the work by Dr. Cynthia Dwork of MIT, who has done all the seminal works in differential privacy and really does a bang-up job of explaining this. If you're interested in her explanations or her papers, many of them are available via Google on scholar.google.com, and others are available on YouTube for review. They're really worthwhile lectures. She's given talks at Microsoft and other places that really go into this topic in depth, and what I'm going to do here is really just a summary of those efforts. So what are we talking about here? We all, as data scientists, became data scientists because we want to learn from data. We want to generate insights from data. And we're used to seeing data in this kind of data frame format that you see there on the left. And you see names and what may be personal information about individuals contained within that data set. And so we want to generate interesting insights from the data, right? We want to learn from the information that's contained in the data. But we also have a responsibility to not harm individuals that are participating in the data. So when we look at large scientific studies about health or about banking, we know and we've learned about bias that can be introduced to those data sets or harmful effects that could result from our analysis. And the example we use is an individual who is a smoker who wants to participate in a health study, and so their data is aggregated in the health study, but is worried about their insurance premiums going up, right? So that'll be kind of our standard example here. So as we work through this, we understand that we want the harm essentially to be limited to the teachings of the data set, right? So if there's an outcome that's a negative outcome, that's okay because sometimes we learn things about negative outcomes. So for example, in our smoking example, in the data set, we want to learn that smoking causes cancer, right? And that as a smoker, you are at higher risk of getting cancer, and therefore insurance companies might want to charge you additional premiums, right? Because you're engaging in known high risk behavior. So you as an individual may be harmed by the findings of our study, but what's important to note here is that what we're protecting against in this differential privacy example is not that you won't ever be harmed, because you would be harmed when your insurance rates go up, but rather that you would be harmed equally whether or not your data was included in the study that helped us to reach that conclusion. So you're harmed equally whether or not the individual is harmed equally whether or not their data is in or not in the data set, right? So a smoker will always pay additional premiums, but that individual smoker's participation in the study was not the cause of them paying additional premiums. Other examples of this might include census data or loan applications and other kind of places where individuals might be in some way affected by the outcomes of our analysis. So some ways to address this that people have used in the past is to say, well, okay, if I want to protect privacy in the data set, I'm just going to anonymize the data set. I'm going to remove any information that would help me to identify any individuals in the data set or would expose to the analyst information that I would want to otherwise protect. That has challenges, and one of those challenges is that it becomes very hard to anonymize a data set in a meaningful way, especially in today's world where there are multiple databases, kind of multiple pieces of information collected about us. And you could easily see how, even though I've removed names and addresses and things that we consider commonly personal identifiable information, you could still, based on the responses within a specific study, narrow down or have some confidence that you're talking about a specific individual. So meaningful anonymization is hard. In order to do anonymization well, you really have to remove a wide swath of the specificity in the data set. And so the other challenge with anonymization is that the data becomes not very useful, right? So in order to protect the privacy of the individual, we have to remove the utility of the data. One other approach is statistical analysis or releasing statistical summaries about data. So you can remove or conduct statistical analysis on the data set and release specific statistics to analysts and say, okay, here you go. this doesn't contain the actual row level information for each user, but it's a good statistical summary. Well, there's a problem here too. So there's this thing called the fundamental law of information recovery that says overly accurate estimates of too many statistics completely destroys privacy. And there are proofs about that as well that we're not going to go into here, but just know that with enough questions about enough data and with enough statistics, you can basically reverse engineer the data set and kind of identify individuals that are contained therein. Okay, so where does that leave us? Well, essentially we have data. We've got a lot of data in today's world, and we want to learn about the population, but not about any individual within the population. So the outcome of any analysis of this data set is essentially equally likely whether an individual is contained in or out of the data set. And that's really the key concept of what we're talking about here. Okay, so just to set up for our conversation here about differential privacy, we're going to be talking about this concept of adjacent data sets. And adjacent data sets are data sets that vary in size by only one record. That is, one individual, let's say, is either in or out of the data set. So you can imagine a data set X that contains a population of individuals, and Y varies from X only by one individual. That is, Y contains all of the same individuals minus one. So these data sets that vary by one record or one row in kind of our data frame construct is the concept of adjacent data sets. Okay, so we have our data sets, X or Y. We've got data, right? And we know that they can be adjacent if they differ in one record. But we also have some other key components here when we talk about differential privacy. We've got our data analyst on the right who wants to ask questions of the data and get answers back. And we need those answers to enable meaningful outcomes and drive utility. And we've got this thing called the mechanism, right? So as we talk through this, you're gonna see something that's labeled M of X or M of Y, and that's essentially the curator or the good guy in our data set, right? And it is going to serve as a randomization function that provides answers out of the data set back to the analyst, right? So it's a trusted entity within this construct, and it's really the tool that's going to be providing us our privacy. Okay, so now that we've got all our components in place, we can start to talk about the definition of differential privacy. And this in specific is called epsilon differential privacy or epsilon zero differential privacy, which we'll go into later. So we've got our two adjacent data sets that we remember differ only in one record, and we've got our mechanism. And so the definition is that if we look at the left side of this equation here, it says the probability that we will see S when M, our mechanism or our curator, asks a query of X is less than or equal to e to the epsilon of the probability that we'll see S when the mechanism asks on Y. And when epsilon is very small, that is the same as saying that the probability on the left-hand side of the equation is less than or equal to 1 plus epsilon, the probability on the right side of the equation. Now, epsilon here is essentially our measure of privacy loss, right? It is a numerical bound that allows us to limit the amount of privacy loss that we're willing to accept when we run a query on this data set. So that's nice in that it allows us to quantify and set a standard for how private we would like our data set to be and enable a description to individuals. Now, it's not mathematically, we're not going to go out and tell people that, oh, I gave you epsilon level of privacy unless you're really into the mechanics of this. But overall, we're quantifying and we're being able to describe how much privacy loss we're willing to accept and how much we're offering with the mechanism that we've selected in our data set. So here's what that looks like in reality. So the probability that we're going to ask a question of the data set and see S of the X data set is shown with the blue line. And the mechanism, the epsilon, modifies those probabilities slightly. And so when we ask that of Y, we can see, and remember Y is an adjacent data set, we can see that most of the time the answers are going to overlap. But there is some area there where we're not going to get the same answer, and that enables us to essentially induce some plausible deniability for the user being in the data set or not. And that privacy loss is bounded by epsilon, right? So we can say, hey, we know that this area here is really what represents the ability to distinguish whether an individual is in or out of the data set. An individual's records are either in or out. Over here, we would get the same answer, right? Anywhere under this curve where these two things are overlapping, we would essentially get the same answer. Whether we asked it of data set X or data set Y, it's really this small region here that represents the difference between the answer we would get when asking of a data set where someone is in it or someone is out of it that would help us. And here's just a function that we call the privacy loss that allows us to say, okay, this is a statement of the probability ratio, and lets us know that that's really bounded by epsilon. So epsilon is our privacy loss value. So the smaller epsilon is, the less privacy risk we're willing to accept. The bigger epsilon is, the more risk to privacy that we're going to accept. And this works in interesting ways. So we can have cumulative privacy over multiple data sets, right? So if the analyst asks a data set that is epsilon 1 differentially private, hey, I'd like to ask you this question, and I get a guarantee of epsilon 1 differential privacy of that data set, and then I go ask another data set that's epsilon 2 differentially private, well, my total privacy loss is the cumulative epsilon total of epsilon 1 plus epsilon 2. It also works on multiple queries of the same data set. So if I'm going into the data set and I've got a query 1 that gives me response 1 and query 2 that gives me response 2, then my probability ratio is less than or equal to e to the epsilon 1 times e to the epsilon 2, which again is cumulative epsilon. Essentially, it's e to the epsilon 1 plus e to the epsilon 2. I'm sorry, e to the epsilon 1 plus epsilon 2. Okay, so what does this mean in practice, right? So what's the intuition here? So essentially I've got the data set and I want to ask it a query and I'm going to get response 1. Well, response 1 has a true value, right? If I say, what's Brian Waite's salary, it's going to come back with a quantitative number. Or if I ask a categorical question and I say, hey, is Brian Waite a smoker or not, it's going to come back and say yes or no, right? So those are concrete values. But what the mechanism is doing here in epsilon differential privacy is it's going to draw on the Laplace transformation, the Laplace probability distribution, and it's going to either randomize or add some noise to the response that it gives you in the case of a quantitative sense, or in a categorical sense, it's going to either lie or tell the truth based on some value in this density function. So the way that this works is, as you can see, these are different visualizations or different realizations of the Laplace probability density function, and we can set different parameters. So we've got the standard deviation of square root of 2 times b, and we know that sensitivity we're essentially going to set to 1 because remember we're dealing with the adjacent data sets, and the most that any individual can change the data set is by 1. And so we're going to use this standard deviation function to insert our epsilon value and kind of define the distribution that we're going to draw from when we're generating the noise to add this privacy. And the way that we do that is we set b equals to the sensitivity, or delta, over epsilon. And then we insert that into this function here, which really sets the width of our probability density function. And so you can see here that, well, let me go to the next slide. So we can see here that if we ask the data set a query and the mechanism responds with response 1, and we're willing to accept kind of a higher level epsilon or a bigger epsilon, which would increase our privacy risk, that means that we're going to get a more accurate answer. So we can see here that the peak of this distribution function is really centered around the true value. And so we know that within some tolerance that the likelihood that we're going to get a value that's very close to the true value is very high. But let's say we were willing to accept less, we're focusing more on privacy, we wanted more privacy, and we're willing to accept a less accurate answer. Well, in that case, we'd get response 2 with epsilon 2, which is going to be much smaller because we don't want to accept a lot of privacy loss. And so that is going to change our standard deviation of the noise generation function, which is this mechanism here. And so the answer that we get back in regards to response 2 could be anywhere under this curve. And as we can see, it's much more likely that it would be varied from the actual true answer here, which means that we're kind of enhancing privacy. Now, what this enables and what's really powerful about this is we still get reasonable answers, right? And in most cases, we're going to get answers that are very close to the truth. We still have this peak in the distribution function, or the density function, but and so our analytic outcomes are still going to be very meaningful, but we're going to enable that plausible deniability for individuals to be able to say, yeah, I was in the data set or I wasn't. Okay, so one final thing to talk about here. So all along we've been talking about epsilon 0 differential privacy, and I haven't really mentioned the 0. I've only been kind of talking about epsilon because the 0 is 0 and it's not really affecting things. But there is another concept that is epsilon delta differential privacy, and basically some people who kind of theorize about this have said, well, epsilon differential privacy is kind of too much, right? It induces too much it gives too much credence to privacy, and we're worried that it's going to kind of affect our results to be non-specific. And maybe in certain cases, in certain data sets, we're willing to accept the risk of additional privacy loss more than what the epsilon allows us to do. And so then that kind of introduced this concept of epsilon delta differential privacy. And that delta essentially just goes on the end of the existing differential privacy equation. So what that does in practice is it introduces a risk that the probability that you're going to expose complete records of individuals goes up slightly. So delta is still extremely small. It's still an extremely unlikely occurrence, but it does allow for some, we'll call it slack in the mechanism to potentially expose the records of individuals in some cases, in some mathematical order of probability. Now, whether that's meaningful or not is kind of up to the user, and that's true of all of this, right? So one of the most important things to understand about differential privacy is that it is a quantification of the amount of privacy loss, but how much and how to manage that privacy loss is still up to you, the user, or you, the populace, or you, the study designer. How much you're going to guarantee to protect people's information is up to you. It really, you could treat epsilon like a privacy budget, essentially. So you could say, I have a privacy budget of epsilon, and I'm going to spend it on one query or multiple queries, because as you implement this, you kind of run into the situation where the more queries you make, the less epsilon you have left over, right? So you have to come up with tools to manage that. You need to be able to say, okay, I'm going to spend half my epsilon on my first query, and then maybe you just keep dividing by half the more and more queries you make. But that's really all has to be designed by your use case. Okay, well, that's really the extent of what I wanted to cover today. I wanted to be able to give you an overview of epsilon 0 and epsilon delta differential privacy, introduce some key concepts, the different players in the architecture, And now you'll be able to go forward with an understanding of how individuals are implementing this and how organizations can make use of privacy mechanisms that enable meaningful analytic outcomes but still protect individuals' privacy to a degree that you've mutually agreed upon. I hope that's helpful, and I'll look forward to any questions you may have in the comments to this video. Thanks so much.